evaporation estimation with a network of field measurements in Northeast and North Africa. This effort was started in 2019 for the purpose of developing consistent evaporation measuring protocols, and also to validate and calibrate satellite-based evaporation under the support of FAO. So I'm just using the field data collected by multiple peoples. As you know, evaporation is the major water balance component and supplying moisture to the atmosphere to sustain rain. It transfers water from vegetation and soil. So characterization of evapotranspiration, spatial temporal distribution is very important for water resource planning, developing efficient irrigation systems. However, accurate estimation of evaporation over a large area requires a lot of ground evaporation estimations. So the accurate method of estimating evaporation is ground data. And on the other side, satellite images provide a big opportunity. They provide the spatial distribution of evaporation over a large scale, but because of the lots of assumption, there is a lot of uncertainty. So in this project, we are trying to validate satellite evaporation estimation using a network of gauged evaporation in multiple countries. And also we have objective of developing a consistent in-situ evaporation measurement protocol across this region. And this shows the study area. Regional evaporation station network was established in 6 countries to obtain reliable ET data to validate remote sensing evaporations. The participating countries. Yes.
Sorry, we don't see your slides. Can you maybe repeat your sharing? Stop and share screen again.
You can't see my slide?
We see just the front slide, the first one. We don't see any other slides.
Okay.
Next one.
No, actually, because it's my presentation right now.
Okay,
No, it's not that. We have some questions. We have slide change the program. We are ready to start now and this is the next one. So as well. Suhaya or Nadia? Nadia and Aya. So anyone can start now and then Aya.
Sorry, I didn't hear. It should be okay. It should be my presentation now. Okay, I'll share my screen.
Okay. Okay. Share your screen, please, and start your presentation.
Okay.
Okay.
Okay. Can you see my screen right now?
Yes, we can see.
Okay, thank you. Okay, so hello everyone. My presentation today is entitled Crop Coefficient and Evapotranspiration Estimation from Synthetic Aperture Radar Data over a wheat field in Morocco. Okay, because there is a problem. Yeah, so as we all know, the water resources in the South Mediterranean are limited, and this situation will further aggravated under the effect of climate change that is characterized by a temperature rising, frequent drought event, and a decrease in the rainfall amount. And among the different sectors that consume water, we have the irrigation that dominates the global water use with up to 90% of the global water use, which highlights the need for a rational and sustainable management of these scarce water resources. And this management requires the estimation at the plot scale of the vegetation water requirement, which is represented by the evapotranspiration. So we'll start with the presentation of the study area. Our study area is in the center of Morocco in the House Plain, which is characterized by a semi-arid climate, characterized by a high reference evapotranspiration against a limited annual precipitation. In a private farm, we have monitored 2 winter wheat fields irrigated using the drip technique and monitored during 2 agricultural seasons, 2016-2017 and 2017-2018. And among the different measurements that were collected over the 2 fields in this study, we have used the automatic measurements from the eddy correlation stations to measure the latent heat flux and the weather station to measure the meteorological variables, and both give us a measurement every 30 minutes. For the satellite data, we have mainly used the Sentinel-1 C-band radar data with a 10-meter resolution and a revisit time of 6 days. We have processed the 2 types of products that exist of Sentinel-1, namely the ground range detected to extract the backscattering coefficient and the single loop complex to compute the interferometric coherence. Briefly, the radar measurement is a complex number whose intensity is the backscattering coefficient, while the interferometric coherence is a measure of the phase stability between 2 successive acquisitions. In this study, you have also used the optical Sentinel-2 images to extract the well-known NDVI. To compute the evapotranspiration, there exists a large variety of models in literature, and the FAO56 is one of the most used models for this purpose. It allows to measure the evapotranspiration as a product of reference evapotranspiration computed from the meteorological forcing using the Pillman-Mantis equation, and a coefficient that take into consideration the real conditions of the crop under consideration. It accounts for soil evaporation using the evaporation coefficient, the plant transpiration using the basal crop coefficient that is corrected from the effects of water stress using a stress coefficient. In this study, we are interested mainly in the basal crop coefficient, which is shown to be sensitive to the vegetation cover fraction and leaf area index. And because of this sensitivity, it was historically derived from optical derived variables such as NDVI, and that using different type of relationships. However, the studies have also highlighted that this application is threatened by the presence of cloud cover. So in this context, our objective in this study is to test the possibility to use the interferometric coherence and the backscattering coefficient as substitute of NDVI to compute the basal crop coefficient. And based on the results of our earlier works, we have obtained a good relationships between radar variables and green leaf area index, and this namely the interferometric coherence and the polarization ratio, which is defined as the ratio of the backscattering at VH polarization to the backscattering at VV polarization. If we look also to the time series over field 1 and field 2 in this figure, we have the time series of NDVI in green, interferometric coherence in blue, and the polarization ratio in purple. And as we can see, the time series show seasonal evolutions that follow the development of wheat. So, and based on this result, we can say that the interferometric coherence and the polarization ratio are a potential candidates to compute or to estimate the crop coefficient. So what we did in a first step, we have computed the ratio of the measured evapotranspiration to the reference evapotranspiration, and the results obtained over field 1 and field 2 for the second season are presented here. we have obtained the typical trapezoidal form of the crop coefficient with a very low values in the beginning of at the sowing date that jump thereafter to a very high values, and this is because of the high evaporation and consequently high evaporation coefficient values in response to rainfall and frequent irrigation at this time of the season. Thereafter, in the middle period, the values are quite higher. And here we can see the effect of stress that is characterized by a very low values. In this study, we have assumed that the data lower than standard deviation to the mean values are stress data. So if we eliminate the high evaporation data and the stress data, the remaining data will correspond to a crop coefficient equal to the basal crop coefficient. So what we did next that we have fitted this filtered data to the polarization ratio, to the interferometric coherence, and to the historically used NDVI. And the results are represented here for field 1 in the first row and field 2 in the second row. Now, if we take into consideration the results from both fields, we can see that the best fitting are obtained using the NDVI and the interferometric coherence. While using the polarization ratio, the relationships are more scattered, and that could be related to the quick saturation of the relationships, in addition that the polarization ratio keep high values late in the season. Now, if we want to compare the results obtained from both fields, we can see that the best results for field 1 are obtained using the NDVI, while for field 2, the best results are obtained using the interferometric coherence. So if we calibrate these relationships over one agricultural season and then apply them for the 3 other seasons, we obtain the results that are presented in this figure for estimating the crop coefficient from the 3 variables, namely the polarization ratio, interferometric coherence, and NDVI for field 1 and field 2. And as expected, for field 1, the best results are obtained using the NDVI, but the performances decreased when we pass to the field 2, and this could be related to the higher NDVI values for this field against a lower crop coefficient values. But if we went to the second field, the best results are obtained using the interferometric coherence. Here, particularly, we can notice a stability in the statistical metrics using the interferometric coherence from one field to another. Now, if we use this estimated basal crop coefficient to compute the evapotranspiration, we have this figure, and we can see that similar conclusions can be drawn as for the last figure. In particular, we have the best results for field 1 with the NDVI and the performance that decreased for field 2, and for interferometric coherence, the best results over field 2, and the stability in the estimate of the crop coefficient are reflected here in the estimation of the evapotranspiration with similar statistical metrics for both field 1 and field 2. What is more noticeable here is also the acceptable result that we have obtained also using the polarization ratio. So now we can, as we have shown, it is possible to use the synthetic aperture radar data to compute the basal crop coefficient, but it is also possible to use the optical and radar data, both of them in a hybrid approach to estimate the evapotranspiration. For example, in this study, we had more than 1 month where the Sentinel-2 images were not useful because of the cloud cover. So what we did, that we have computed the crop coefficient from the interferometric coherence for this period when Sentinel-2 images are not available, and estimate the crop coefficient for the rest of the season using the NDVI. And the results are presented with statistical metrics in this table for the method using NDVI and for the hybrid approach. And that's for field 1 and field 2. And as we can see, there is an obvious improvement in the estimation when using the hybrid approach. for the all statistical metrics, but for example, for the correlation coefficient, we have here an improvement in over field 2 of up to 16%. There is also a decrease in the bias with 27% over field 2 and up to 60% for field 1. So if we want to conclude, in this study, we have tested the possibility to compute the crop coefficient and consequently the evapotranspiration using synthetic aperture radar data from Sentinel-1. And our results have shown that this data can be successfully used for this purpose. In particular, the interferometric coherence that demonstrates a good performance and particularly a stability in the statistical metrics from one field to another and from one season to another, which implies the possibility of a robust and operational applications at large scales, especially in cloudy regions or simply in winter when the optical data are not available for long periods. We have shown also that it is possible to use radar as a complement to optical data. For this study, the most shortcoming that was observed concerning the use of radar data was an overestimation at the end of the season. But however, this is not important for water requirement or for vegetation water requirement applications, as the vegetation dries out at this time of the season. In addition, that the irrigation is already stopped. However, this work is first of its kind and it's a first attempt at estimating the crop coefficient and consequently evapotranspiration from synthetic aperture radar data. But further research is obviously required, and that's for further validation in order to deepen our investigation and our understanding of the relationships between the basal crop coefficient and radar and optical data behavior, and that in view of different geometrical and physiological effects. It is also required to extend the validation or also to test over other annual crops and using different irrigation techniques. One of aspects of our current work is the partition of evaporation using water balance and transpiration components that should be also corrected from the effect of stress using the stress coefficient that can be computed from thermal data, and that will be more interesting in the view of the launch of the future missions with high spatial and temporal resolution that will be close or similar to those of Sentinel-1 and Sentinel-2 spatial and temporal resolution data. It is also important to deepen or to investigate the effect of surface soil moisture on the interferometric coherence, as this will impact the relationships with the crop coefficient, and thus require a sub-daily measurement of radar data. Fortunately, we have a Mokhtar experiment, which is an in-situ radar that is installed over a wheat field in Morocco near the Shishawa city, and that allows the measurement of the interferometric coherence and the backscattering with a time step of 15 minutes. And these data are currently under investigation and will for sure used in our future works. And that's all, and thank you for your attention.